The VC dimension can measure the complexity of our hypothesis set. So this is formal definition of VC dimension. So let's say the set system X and hypothesis set H. So this is input domain and this is our hypothesis set that consists of a set X, which is input domain, and a collection H, the hypothesis set. And here we are consider binary classification tasks. So the output is 0 or 1. And so we can represent each hypothesis defined on input X as a subset of X, right? So the subset indicate the function having value 1, right? So for instance, if X is 0 and 1, and your hypothesis is 0 is indicate 1 and 1, the output corresponding output is 0. That is our hypothesis. If then the subset of H, that subset of X that represent the hypothesis is this singleton set, right? So we can represent a hypothesis class using subset of input domain X. And for any subset of X denoted by A, the projection of our hypothesis set on A is defined as follows. The overlapping between the given function at given subset A and each hypothesis H. A set system X and H shatters a set A if each subset of A can be expressed as the overlapping between A and H for some hypothesis H. That means the cardinality of HA, the projection of H on A, is equal to the cardinality of A, which means the projection of H on A include all possible subset of the set A. Okay, the shatters means we can express every possible functions or possible mapping by using our hypothesis set H for a given set A. Then we say our hypothesis set shatters a set A. Okay, and this shattering concept is important to define the VC dimension. So here the VC dimension of hypothesis set H is the size of the largest set shattered by H. That is VC dimension. Okay, so formally that is supremum of your subset A that can be shattered by your hypothesis set H. Okay. So graphically, I will show you what is the meaning of shattering. So when we have a set A having these 4 points, and if our hypothesis defined with a box, so if input point belong to inside of your box, then the point having output value 1. Outside of the box, then the value, the corresponding output value is 0. Okay, so we can think that kind of hypothesis with a rectangle or box. And with the box, we can shatter these 4 points. So we can make this 1, 1, 1, 0, 0. And we can also define 1, 1, 0, 0 using this box. And we can define this box to denote 1, 1, 0, 0. And so on. We can define any subset, or we can include any subset of these 4 points using rectangle. So we can say the rectangle hypothesis. So all the inside point inside point of a rectangle having value 1, outside of the rectangle having value 0. that kind of hypothesis set can shatter 4-point, at least for this case. Then we can say the VC dimension of this rectangle hypothesis is at least 4. It is okay, there is some case having 0.4 and we cannot shatter this 4 point. It is okay. It is okay. Some cases 4 point cannot be shattered by our hypothesis. It is okay. So in the definition, we are saying the VC dimension is defined with the largest set shattered by the hypothesis. So if there exists at least one special case that can be shattered by our hypothesis, then it is enough to say the VC dimension. Okay. So these are examples of VC dimension with different hypothesis set. So I'm gonna skip this right now. But if you have any question to make this hypothesis by yourself, then please use our Q&A board in Discord or KLMS if you want. Okay, so to understand to connect the VC dimension and our sampling complexity theorems, we need to understand the growth function with respect to the VC dimension. So how many hypotheses can be defined on finite number of input with our hypothesis set. So that can be defined with this Shatter function. The Shatter function, this pi hn for system xh is the maximum number of subsets A of size n that can be expressed as A and intersection with H for each H. Okay, so how many different functions can be defined on subset A using the given hypothesis set H. Okay, so that is more formally defined as follows. So again, this is for the case the best scenario of subset A having subset size n. So again, it is okay. There is some very bad case, the subset A having element n element, but the number of hypotheses can be defined on A is 1 or 2. That is absolutely fine. We are considering just max, so we are considering the best case, having the largest possible number of different cases. So from the definition, when the cardinality of x is equal to n, and the n is finite, the cardinality of h is equal to the Shatter function, okay, with n, okay, from the definition, because here we consider the entire set, and the entire set size is n, so that is from our definition. Right. And to understand the growth functions, so how this growth function grows with respect to the VC dimension, we have to introduce Sauer's lemma. And before introducing the Sauer's lemma, I want to define some mathematical notations. So I will use this and choose greater than or equal to less than or equal to d is equal to summation of n choose 0 plus n choose 1 plus plus up to n choose d. So especially for n is smaller than d, then so it is real not well defined, right? Because n choose d, when you write down this, the underlying assumption is D is smaller than or equal to N. So when D is strictly larger than N, this is a little bit not well defined. So in this case, we just say N choose less than or equal to D is just a 2 to the power 2 N, which basically ignoring the case D is strictly bigger than N. Okay, so when you sum up from N choose 0 to N choose N, which is exactly 2 to the N, right? So for N is strictly less than D, we just simply ignore the not well-defined terms. So we can easily show that when N is strictly bigger than D and D is greater than or equal to 2, there is some relationship like this. So this we can easily show, and so for your convenience, I write down the relationship between N choose less than or equal to D and some very interesting inequality. So we can derive this inequality from here, right? So this is the Sauer's lemma. For any set system X and H, so this is the input domain and this is our hypothesis set. For any set system and having VC dimension and most D, then the growth function value can be upper bounded by N choose less than or equal to D, what we just defined. And from the last inequality properties, this is upper bounded by this and this is upper bounded by this. So when we know the VC dimension, we can basically upper bounding the number of hypotheses defined on our input domain X. So when VC dimension is very small, we don't need to worry about this scale of increase of possible hypothesis set. 2 to the N is all possible hypotheses can be defined on input domain X. But if we consider, when we consider very, very simple hypothesis class, mostly we cannot cover such all possible hypothesis functions. Instead, we just we can define very tiny portion of all possible functions. And the Sauer's lemma and VC dimension tell us such the number of possible hypotheses on your input domain. When VC dimension is small, we don't need to worry such exponentially grows. We just having N to the D number of hypotheses in our domain. Okay. So when you go back to packed learning theorems and all the results what we have driven last weeks, we use union bound, and at that time we multiply some concentration inequality by the number of hypotheses. Here, since we can upper bounding the number of hypotheses defined on our input domain using Sauer's lemma and the VC dimension, with such a union bound result, we can get tighter bound. So even if we have infinitely many hypotheses, when we have finite input domain and when we have finite VC dimension, essentially the number of hypotheses defined on our input domain can be easily upper bounded by this polynomial. Right. Good. So how to show this Sauer's lemma? So this is the proof of Sauer's lemma. So we first consider very trivial case. When n is less than or equal to d, this value is just 2 to the n from the definition. Then the Sauer's lemma holds because this means all the possible functions, right? This means the number of all the possible functions. So this definitely less than or equal to 2 to the n. When VC dimension d is equal to 0, by the definition of hypothesis class H and the VC dimension, H is just empty set because VC dimension 0 means we cannot make any discrimination even for single input data point, which means the hypothesis class is just empty. So we have a zero hypothesis. So we have this trivial bound. Right. Okay. So now we consider general cases. The proof strategy is mathematical induction. We first assume that this is hold for the case n-1 and d. And then we show that when this hold for n-1 and d, n and d case also true. Okay. So to this end, let's define A, which is subset of input domain X, having a set size n. And we say this is the best case subset, which make this growth function equal to the cardinality of the set defined by overlapping between A and hypothesis, each hypothesis. Right. Just for this proof, let's redefine H as follow. When we have H1 and H2 in our hypothesis set, such that the intersection between A and H1 and H and H2 are the same, we keep only one of them in H. So basically we project our hypothesis to set A. Okay, then the cardinality of H is equal to the growth function. And consider one single element of A, and for the selected element U, we define two subsets of A minus the singleton U, which is H1 H1 hypothesis set and H2 hypothesis set. H1 is just simply remove the singleton U from each hypothesis. H2 is a little bit more complicated. So we include hypothesis such that the hypothesis does not include the element U, the selected element U. But the union of hypothesis and the singleton set also element of our hypothesis set H. Then every H defined on A minus U satisfy one of the following conditions. When only one of H and H union U belong to H, original hypothesis set H, then let's check whether H belong to H1 or not. So when only this one is true, then which means H does not include the element U. So H minus U does not change anything. So this is H itself. Okay? And also H belongs to the original hypothesis H. This is true. Right? So H also a member of H1. Let's check whether this H is a member of H2 or not. When only this is true, then this is not correct. When only this is true, when only this is true, then this does not correct. That's it. Right. So when only one of these conditions belong to original hypothesis H, H is in H1 only, and H is not member of H2. When both H and H union U belong to H, the H is an element of both H1 and H2. Okay? Let's check. When H and U both belong to H, then it is okay to remove U. Right? And when both are true, this is hold and this is hold. Right? So we can say that H is a member of H2. Of course, here H and H union U, they are not the same. Here we consider hypothesis which a member of A minus U, so which is a subset of A minus U. So H does not have U as the element, so H and H union U, they are different. And so when both are the member of original hypothesis H, then we can say the H hypothesis is an element of both H1 and H2. Then we have the cardinality of H is equal to the cardinality of H1 plus cardinality of H2, because so there is H1 set and there is some H2 set, right? This is the case. H and H union U belong to H. And all this area, the H2 area, is the case of the second case. And this intersection part will count twice. And in that case, we have this property. Both H and H union U belong to H. Right? So what does that mean is each part of this element will make a corresponding hypothesis either by H itself or H union U. But for the case for this union case, both are possible. So we can generate two different hypotheses from one single element in the union, in the disjoint, in the joint part. No, in this area, this intersection area. Sorry. Okay. So the sum of cardinality H1 and cardinality H2, which basically counts this intersection part twice, but that is fine because this part, this intersection part, generate two different hypotheses by using the hypothesis itself and hypothesis and U union. Right. And that's why the cardinality of original hypothesis is equal to the cardinality of H1 plus the cardinality of H2. So we now consider the BC dimensions of A minus U H1 and A minus U H2. Let's consider the BC dimensions of A minus U with hypothesis set H1 and A minus U with hypothesis set H2. Right. So every each hypothesis H makes different intersection with A, original set A. So in other words, when we have different hypotheses H and H prime, then the intersection between A and H prime, they are different. Therefore, the cardinality of H2 must be less than or equal to the growth function with number of samples n minus 1. Since all hypotheses in H2 make different intersection between A minus U and H, and A minus U have element n minus 1, different element. Then by the definition of this growth function means the maximum possible function defined on any set of which size is n minus 1. Since this set has element n minus 1 element, the cardinality of H2 must be upper bounded by this growth function with n minus 1 element. Okay, so this is growth function for H2. And when A minus U union H1 minus U is equal to A minus U and H2 minus U, then essentially we have H1 minus U equal to H2 minus U. When H1 and H2 in our hypothesis set. Okay. So, which means the cardinality of H1 is again less than or equal to the growth function with number of elements n minus 1. So from the above two facts, we have that the growth function for n elements by definition was equal to the cardinality of our original hypothesis h, which was equal to the cardinality of h1 plus cardinality of h2 from the definitions of h1 and h2. And since both h1 and h2 are defined for the n-1 element case, by erasing the singleton element u, we can upper bound the h1 cardinality by the growth function of h1 with number of elements equal to n-1 plus the growth function for h2 with n-1 elements as well. Okay. Now let's discuss the VC dimension. Under the condition the original hypothesis set H having VC dimension D. If the original hypothesis set has VC dimension D, then both H1 and H2 have some limitation. So if H1 can shatter a subset of A minus U of which size is D plus 1, which means the original hypothesis H can also shelter a subset of A having size D plus 1. But since the original hypothesis set H has VC dimension D, this is not possible. So the VC dimension of A minus U H1 is M most D. If B is subset of A minus U with cardinality B is greater than or equal to D, which can be shattered by H2, then B union U is also shattered by the original hypothesis H. Then this means the original hypothesis that H can shatter D plus 1 element, which again contradicts with our main assumption, the original hypothesis VC dimension is equal to D. So therefore, the VC dimension of A minus U H2 is less than D minus 1. Okay, all comes from the definition of H1 and H2. And from the definition of H1 and H2 and the assumption our original hypothesis VC dimension is bounded by D, we now have VC dimension as well. Okay, so this growth function should be upper bounded by n-1 choose less than or equal to D because it has n-1 element and VC dimension is D. And the growth function with respect to H2 is upper bounded by this because we have n-1 element and of which dimension is upper bounded by D minus 1. So we finally have the growth function is less than or equal to this. And this summation is exactly this. Oh, okay. By the way, these are true because we are using mathematical induction, and for the mathematical induction, we assume that it is true for the case n minus 1, right?